Good morning. I'd like to introduce Benjamin Steinberg from City College, and today he will be talking something about semigroups.
Yes, thank you.
We lost by 10 seconds.
So I'm going to talk about the representation theory of monoids with basic algebras. That's what I think that's the title was. So basically, there's going to be 3 parts to my talk. The first part of my talk, part 1 will be like, what are basic algebras and why do people in representation theory study them? The second part would be why monoid representations, meaning why anyone would care. And part 3 will be actually something about, but part 3 may, if there's enough time, part 3 will be about what I've actually done. But I find that half the time you don't get up to part 2. So what I did is joint work with Stuart Margolis, who the camera cannot see, but he's here in the audience. But Stu and I did. That's part 3 if we get up to it. So this will be actually what the representation theory of these monoids that I care about are. But first I will try to convince you why people care about these things. Alright, so let's try purple. There are only 3 colors here and this seems to write the best. Okay, so in this talk, all algebras are over C just to make our life simple and no complications. A is always going to be finite dimensional algebra over C with unit. Okay? That's always going to be the setting. I'm slightly lying. There will appear one type of algebra which is not finite dimensional, but you'll know it when it comes. Okay. So now let me give you sort of a proposition / definition of what is a basic algebra. So I'll give 3 equivalent characterizations of them and then say this is what's called a basic algebra. I don't know if everybody I know this sort of seminar is fairly general, so I don't know if anybody or everybody has seen basic algebras, or so that's why I'm saying this. So the following are equivalent. This is really a weird color. The following are equivalent, but it's the only one that writes dark for A. A being finite dimensional algebra of this sort. Number 1, all the simple modules are one-dimensional. Number 2 is, if you factor out by the radical, that's isomorphic to a product of copies of C. The radical just the largest nilpotent ideal. And number 3, A has a faithful representation by upper triangular matrices. Okay, this color is just too weird.
I think blue also works well.
No, that was the blue.
Green was not good.
I can try green. Blue is pretty bad. Black would be nice, but there's no black. I'll try black. Maybe on the next board. I don't want to mix the colors. That will just make the camera. People are going to be adjusting their little YouTube color controls to figure out what the heck happened. It looks kind of like the New York Giants colors, right? We have the red and blue. Okay, so these are the equivalent conditions, and A is basic. I'm sorry, I've lost my voice a little bit. If it satisfies these conditions. Okay, so being basic just means all your irreducible representations are one-dimensional. So maybe I'll give an example. You can take Tn, which is just n by n upper triangular matrices. That's obviously has a faithful representation by upper triangular matrices. The other example is you can take the group algebra CG, where G is abelian. Actually, it follows right from the definition that a semi-simple algebra is basic if and only if it's commutative. So the only group algebras which are basic are algebras of abelian groups. For finite groups. G is, of course, all groups in this talk are finite. Okay, so now I'll try green. And then we'll vote which color is the most legible. This looks like a quotient, so I'll try this one. All right. Well, we'll see more examples in a minute. So why basic algebras? Oh, this one is good. Other than it looks like the Jets. So why basic algebras? So it's a classical result that I don't actually know who proved first, or when it was proved. The textbooks never seem to attribute it to anybody. But it's a classical fact that, well, first let me recall a definition. Recall that A and B are Morita equivalent. If the category of, say, left A modules is equivalent to the category of left B modules. Doesn't matter whether you do left or right. Also doesn't matter if you restrict to finite dimensional modules or arbitrary modules, it's the same. This is called Morita equivalence. And it turns out that every finite dimensional algebra is Morita equivalent to a unique basic algebra up to isomorphism. So in other words, the basic algebras give you sort of a canonical set of representatives of the Morita equivalence classes. So it's a theorem, I think it's older than Gabriel, but maybe it's Gabriel, I'm not sure. It's probably older. The theorem is each finite dimensional algebra is Morita equivalent to a unique basic algebra up to isomorphism.
It's probably that.
Black one. Uh-huh. All right. That's a little bit worse. It's worse? The green's better?
Make sure that you can remove that ink again. You might not be able to remove it once.
Press harder, maybe.
Press harder?
It might be like a permanent
Like
sign. That happened once.
Press it, erase.
Yeah, make sure that it erases.
Oh, you mean it says it's a dry erase.
Oh, okay, yeah, that's fine. Because I remember once something like terrible happened.
Oh, yeah, I had that in Paris. I ruined somebody's blackboard and thought this is.
So when I say unique, of course, up to isomorphism. So in other words, so if your definition of representation means the study of the category of modules, then you can just freely assume that you're dealing with basic algebras. And most modern books on the representation theory of finite dimensional algebras do that. However, if you're a finite group theorist, then your definition of representation theory is orthogonal to this, because the module category of a finite group tells you only the number of conjugacy classes. Basically, you don't include the tensor product. If you just view it as a category, it tells you nothing but the number of conjugacy classes, which is only sort of interesting, I guess, if the group is abelian, and even then not so interesting. So this viewpoint of module categories is orthogonal to classical finite group representation theory, where the only thing you care about is the structure of the simple modules. The category, the simple modules, are black boxes that are connected in some ways, right? They don't actually care the structure. That's why you can cut it down to one dimension. So I should just warn you that there's something to be worried about. Okay, now it turns out there's a very nice way to construct all basic algebras due to Gabriel using quivers. So let me just remind you what is a quiver, a path algebra, and how you get basic algebras from that. And then I'll get to the next topic. So maybe this is known to many people here, maybe it's not. So let me just remind you. So a quiver is a directed graph. Right. Apparently, if you're famous enough, you can just give a new name to a well-known object. So a quiver is just a directed graph. And in this talk, they're always finite. Okay. Now, if Q is a quiver, you can define the path algebra, which will not be finite dimensional. That's my one exception. The path algebra CQ has basis all directed paths in Q, including an empty one at each vertex. Okay? So you take as a basis all paths in the graph, directed paths, including an empty one at each vertex. And you multiply by concatenating paths when it makes sense. And if it doesn't make sense, you say it's 0, and then extend it linearly.
I don't understand why it could be infinite dimensional. Don't you have a finite number of paths?
No. So here's example.
Oh, you're allowing...
Loops, it doesn't have to be
okay.
acyclic. It's a finite dimensional if and only if the graph is acyclic.
Oh, okay.
So for example, if this is your quiver, then CQ, this is Q. CQ is just a polynomial array. which is definitely not finite dimensional. On the other hand, if you have an acyclic quiver, it will be finite dimensional. So if I do this, Q is equal to this, then CQ is finite dimensional, and it's isomorphic to 3 by 3 upper triangular matrices. Oh, sorry. I have to orient my quiver. So this would be isomorphic to 3 by 3 matrices. I'm counting correctly. So in general, the path algebra is finite dimensional exactly when the quiver is acyclic. Okay, now let J equal the ideal generated by the arrows, or edges. They call them arrows since it's called a quiver. So it's the ideal generated by paths of length 1. Then an ideal I in CQ is called admissible. If you can sandwich I between some power of J and J squared. That's the terminology. And then the fact is that if you take CQ mod I is going to be a basic finite dimensional algebra. That's A. I don't know, fact. This is really a theorem of Gabriel. This part's a fact, but the second part is a theorem. This part is not difficult. The difficult part is part B. So number 1, so you get a basic algebra by taking a path algebra and killing an admissible ideal. And B, that's how you get all basic algebras. All basic algebras are of this form. And the quiver Q is unique, but not the ideal. Above, for unique Q. So all basic algebras look like a path algebra, but quiver, modulo, and admissible ideal. And the quiver is unique, the ideal is not. And so this is why, so you see all this quiver stuff going on in finite dimensional algebras. And they sort of spread out like a disease into cluster algebras, Lie algebras, and everything else under the sun.
And given a quiver, fixing a quiver, do you get different basic algebras depending on the ideal?
It depends on the ideal very much. In fact, basically this number n, the smallest n that works is like controlling the radical length. So that's going to give you the power of the radical that dies. So your radical is just going to be the image of I, sorry, the image of j after you factor out I. So the jn will become 0. So now it's a different algebra. For instance, if you do it on this quiver, an admissible ideal just means an ideal of the form x squared, x cubed, or higher. And so essentially you're just getting these nilpotent kind of, well, not necessarily nilpotent because it's a 0 polynomial. They're polynomials of degree, you know, at least, well, it has to be contained in j squared, so at least 2. The 2 is important. Okay, now let me just tell you what is Q so that if I have time later you can see what we're trying to compute. So although the theorem says, I should say, that your basic algebra looks like this, and all guys who write papers on finite dimensional algebras assume that it's already of this form. So they would call the pair Q and J a quiver presentation. Maybe I should say Q, J is called a quiver presentation. QI. Oh, is it I? Sorry, you're right, it's I. QI is a quiver presentation of your basic algebra. J was fixed, yes, I got my J and my I confused. Okay, so, but they always assume you have this. Now, if I give you a finite dimensional basic algebra by some other way, it's not so easy to find this. It can be done in principle because you can do linear algebra in like dimension the size of the algebra, but A, that's not enlightening. When you get an answer, you don't really understand it. And B, it's not useful if you have a sequence, say, of algebras and you want to know what it looks like for all of them. Okay, so what is Q? And then I will move to part 2 of the talk. So vertices of Q is equal to simple modules for the algebra for A equal to CQ mod J. Okay, when I say simple modules, I mean isomorphism classes of simple modules. And the number of arrows from, say, S1 to S2, this is the dimension of X1. I'm not going to write the name of the algebra. Between S1 and S2. So remember, X classifies the short exact sequences of this form up to some equivalence relation that preserves this sort of filtration. Now, these are one-dimensional modules because it's a basic algebra, so this will be a two-dimensional module. Conversely, every two-dimensional module is an extension like this for some simple modules. So the quiver is like an encoding of the two-dimensional representation theory of the algebra. And it's clearly a Morita invariant, so it therefore is uniquely determined. Okay, there are other ways to describe this in terms of primitive idempotence that I don't want to get into. This is the one that we always use. Okay, so if you have a basic algebra and you want to use the modern representation theory to do something with it, you have to know how to compute this quiver, and then you have to know how to get the relations. Now the relations can be tricky if you use this form of quiver. Okay, so that's basic algebras, where they come up in representation theory and why people study them in quivers. Any questions before we move on to part 2?
Well, it may be a side issue, but the quiver algebra is a bi-algebra, and probably a half algebra too.
Not a half, but it's bi. I guess.
I think you can.
Yeah, you can put a half thing. You can do something like break it up.
Recursively.
Yeah, you can do this.
But on the other hand, unless I misunderstand it, J and I are not going to be co-ideals. No. They're not compatible with the co-multiple.
No, not in general.
Because when you cut the pairs, you're
going
to get pairs of...
Yeah, basic algebra doesn't necessarily have some sort of natural bi-algebra structure on it. But yeah, you can do the same thing you do with the free algebra. You can make the same kind of like co-commutative algebra structure, whatever it's called, where you break words into two parts and add it up, or shuffle, because you could probably do some variations. Yeah, I think that's no problem. But yeah, anyway, nothing's going to descend to this. Even it's off. Even the quiver path algebra is also graded by like the path, but this ideal doesn't have to be homogeneous.
That's right. Yeah,
so sometimes it is, but often you lose a lot of structure. Okay, so now monoids. Right. So we all know. So all monoids are finite in this talk, except for ones which have to be accidentally rings. Okay. So everyone knows, I assume, a monoid is a set with an associative multiplication and an identity. Okay, so first of all, why care about monoid representation? Okay, well, believe it or not, once upon a time it was a question, why care about group representation theory? It's very famous that Burnside, in the first edition of his book, wrote that there's nothing useful you can prove with group representation theory that you can't use permutations to do, and therefore I'm not including it. And then, of course, in the second version of his book, it's dedicated to all the basic theorems of representation theory because he discovered lots of important theorems you can use it for. But eventually, nowadays, group representation theory is as much used outside of group theory as it is used in group theory. It's used in physics, it's used in probability theory, it's used in engineering. It's essentially discrete Fourier analysis. Now, in semi-group representation theory, a semi-group theory is not as well studied as group theory, and the kinds of questions people study usually come from computer science, where representation theory doesn't seem so relevant. But in recent years, particularly beginning with a nice paper in 1998 by Bidigare, Hanlon, and somebody I found out almost was Dean of Science at Sioux City College, but I guess didn't get the job because I don't know why. And Rockmore
studied semigroups.
Maybe. So this was a paper in the Duke Math Journal in 1998, where they applied semigroup representation theory for a very almost trivial class of semigroups from a semigroup viewpoint to studying random walks and Markov chains. And they showed that the representation theory of the semigroup lets you analyze all these Markov chains in a uniform way, and that gives understanding that people didn't have when they did ad hoc techniques or even group theoretic techniques in some cases. So basically, they found applications to Markov chains of semigroup or monoid representation theory. And then this was taken up further by Diaconis and Brown. I should mention none of these people are semigroup theorists. And then later by Brown. This is Ken Brown, the famous group theorist at Cornell. Brown's a pretty common name. Diaconis is not so common. Probably there's only one person Diaconis. There's actually more than one Ken Brown if you look on MathScience. There's Kenneth S. Brown and then there's our Ken Brown. Whose middle name I don't know. Or maybe he's the S and the other one's the F. There's a Ken A and a Ken S. Maybe ours is the F, I don't know. Anyway, then Diaconis and Brown, then Anders Bjorner wrote a couple of papers on this. Recently, Ron Graham and Fan Chung have written papers using this, analyzing Markov chains with this stuff. So very well-known people in combinatorics and probability theory started to study representations of a very simple class of semigroups in order to analyze Markov chains. The problem is, it was classical. I guess Diaconis is the guy who really made it popular to study Markov chains on groups using representation theory. But the thing about group Markov chains is they're very limited. The stationary distribution has to be uniform. If you do a random walk on a group, you'll get a uniform distribution of stationary. And so if you have a Markov chain which has a non-stationary distribution, you're out of luck. But it's a fact that every finite Markov chain is a random walk of a semigroup acting on a set. And therefore you can always use semigroup approaches. And also, sometimes semigroup representation theory is easier than group theory, because I told you a group algebra is basic if and only if it's abelian, which is, if you look at Diaconis' book, that's the easiest case. But semigroup algebras can be basic all the time, lots of examples. They can have very nice to analyze representation theory. Okay, so let me tell you very quickly what is a Markov chain, so that you can see why semigroups get involved. I'm not going to give you the definition you'll find in a probability book, but the definition I'm giving you is equivalent. It's what's called the random mapping representation. Or said differently, the cone of stochastic matrices has extreme points, the function matrices. That's the fancy way. Okay, so what is a Markov chain? Finite state Markov chain. Alright, so here it is from our point of view. You have a finite set X. These are the states of the chain, which you can think of where the particle could be, or the possible orderings of your deck of cards if you like to shuffle cards like Diaconis does. We have an action of a monoid on X. Again, always finite. You can assume the action is faithful if not important. You have a probability distribution, which I'll just call probability on M. So that means you assign a probability to each element of M so that it adds up to 1. We don't need to talk about measures in the finite case. And we have a probability, I guess I'll call it mu0, a probability on X. This is what a Markov chain is for us. And what does it mean? So intuitively, you imagine your particles at some state in X, or maybe some distribution of states. This mu0 will be the initial distribution of where the particle is likely to be. And then you randomly choose an element of your monoid according to P, and you act by that element. And that tells you where the particle is going to move. Of course, it gives you a probability, so what you're going to get really is a new probability distribution. So it's sort of like a stochastic dynamical system. So you randomly choose a monoid element and you act by it. Every Markov chain has such a representation. The monoid is not unique. Okay, now how does the system evolve? I'm going to tell you in purely algebraic terms. So this is monoid. This is Markov chain theory for algebraists. You'll never find it written any book this way, but it is equivalent. Oh, that's just the wrong side. Okay, so here's the trick, and this is why representation theory is useful. Identify P as an element of the monoid algebra. Everybody, monoid algebra is defined like a group algebra. Okay, so what we do is we set P to be the sum over all guys in the monoid of the probability of choosing that guy times the guy. Right? So Pm is just the probability of M, of choosing M. Right, so P is really a distribution of an M-valued random variable, but I don't want to give this kind of language. Actually, this is little m. Okay. Okay, similarly, I can view my initial distribution as an element of a vector space with basis x, right? Just in the same way. Just the px, qx times x, so the same way. Okay.
So x is finite.
X is finite, yes.
Yeah, yeah.
X, oh, everything is finite. There's a finite state Markov chain. Yeah, no, I don't do anything infinite in this talk. C is the only infinite thing causing infinity to appear in this talk. If C wasn't infinite, life would be easier. Okay, so similarly this I can view as an element here by just taking a linear combination of the guys of x, weighted by their probability. So then I can define the next probability, the next step, transition probability, to be just P times mu0. What does this mean? Cx is clearly a Cm module because m is acting on x, so it extends linearly. Therefore, this operator can act on that, and I get a mu1, which you can easily check as a probability. And similarly, in general, we can define mu(n) to be p mu(n) minus 1, which is just p to the n mu0. So analyzing this Markov chain is the same thing as analyzing the powers of p, which is an element of the semigroup algebra acting on this module. Okay. Now, I think maybe in the interest of time, don't want to give too much detail, but maybe I'll say, so what do probabilists want to get out of this? They want what?
For Friday.
Okay. Well, so, under mild assumptions, which I won't tell you what they are, you get that this sequence of probability distributions converges to something which everyone always calls pi. And the key property of pi is that p pi is equal to pi. Pi is called the stationary distribution because it's stationary. It doesn't change under the process. Okay, so what do probabilists want? So they want to know A, what is pi? Sometimes it's easy to see what it is. Like if M is a group, it's easy to see what it is. B, how fast does this convergence? That's what they really care about. You want to know when you shuffle a deck of cards, how many times you need to shuffle it. So how fast is convergence? Other things you want to know, this is C not E. Is this matrix P diagonalizable? Or the operator P. Is the operator P diagonalizable? At least on C of X? And they want to know the spectrum of this operator. What are the eigenvalues? Because you're computing power, so that's something you would want to know. So these are the kinds of things that they want to know. And representation theory can help you. So a typical example, I'm not going to write it, is you can imagine X is all possible n factorial orderings of a deck of cards. M is the symmetric group. And P is the distribution that comes from riffle shuffling a deck of cards, which is called the Gilbert-Shannon-Reed distribution. And then you're analyzing shuffling a deck of cards, which is a random walk on the symmetric group. Okay, I don't think I'm going to try to give too many examples. So let me sort of tell you, why does representation theory help?
Do you have a simple as an example where it's a monoid?
Yeah, I just gave you an example.
Oh, I thought, oh yeah.
That's a group.
Oh, you want one which is not a group?
Yeah, that's what I meant.
Okay, yeah, all right. Okay, here's a simple example. It's called the Settlin Library. This was the main one that the guys in Bidigare, Hanlon, and Rockmore were analyzing. So the states are, you're going to argue me this is a group. Sn, but it's not a group. No, actually, words, so viewed as words, viewed as linear orderings. So in other words, I don't view them as functions, I view them as 1, 3, 2, like that kind of thing. Okay, and the Markov chain is, you have a probability P going to be sum over I equals 1 to n of pi. I'll write it the probability way. Take the delta. Delta I just means the probability 1 at I and 0 elsewhere. So this is just, you give weight with probability pi, you choose I. And now what you do is, with probability I, you move I to the front.
Probability pi.
Pi. You move I to the front. So the way you're supposed to think of this is you have a shelf of books with titles, let's say 3, 2, 1, 4, 5. Those are the titles of the book are the number. And every time you take a book out, you put it at the front. So that way, all your favorite books will be at the front, all the books you never use are at the back, and you know roughly where to find your book, even if you don't have time to organize your bookshelf. Okay, so for instance, if I choose out 1, so if I choose 1, say, then my next state will look like 1, 3, 2, 4, 5. Now this is not a group thing, because if my thing looked like this, I would also, if I didn't mess up, get 1, 3, 2, 4, 5. So the monoid, these transformations that do this generate a monoid, which I can write down explicitly what it is, but I don't want to spend the time doing it. So it's a monoid. It's known that this is only a random walk. This can be expressed as a random walk on Sn only when this is a uniform distribution. When it's a uniform distribution, it's the same as taking a deck of cards and shuffling by taking the top card and shuffling it into a random spot. Except it's actually the dual of taking a random card and putting it on top. But if it's not uniform, this has a non-uniform distribution as the stationary. So it cannot be gotten by a group. You can get a Markov chain using a group if and only if the stationary distribution is uniform. That's Birkhoff's theorem. Okay, so that's the example that they cared about. Okay. So why does representation theory help? Okay. Suppose M is a group. As I said, I don't know how much I'll get into my stuff because I have to actually explain why you would do what you're doing before you actually do it. Just to make life easier. Okay, then our module Cx will break up into a direct sum of irreducible representations. Right? If M is a group, that will happen. That means that my operator P will have a diagonal form, P1, P2, P3, Pm. And clearly, to understand the powers of P or the eigenvalues or whatever, I just have to understand these. So I just have to understand what these elements are doing in the irreducible representation. So I'm doing Fourier analysis. If G is abelian, then these irreducible representations are one-dimensional. This is exactly when the algebra is basic. So instead, what I'm going to get is P is going to look like this. This is supposed to be a chi. I get all the characters applied to my operator P. And this is actually a diagonal matrix. So I just proved for you that the group is abelian, the random walk is diagonalizable. Completely trivial. But this is the kind of thing they used to prove by brute force before they realized they could use representation theory. And what is chi1 of P is it's just the sum over G in my group G. I'll put it into G, a group now. So we call this lambda chi1. So for each character you have an eigenvalue and you know exactly what it is. Okay. If M now as a monoid has a basic algebra, the same works. The only difference is, to save time, I'm not going to rewrite this, I have a star here. But for the eigenvalues, who cares? Eigenvalues doesn't care about upper triangular. It will be upper triangular. So if you have a monoid, you don't have a direct sum of irreducibles, but you have a composition series. The composition series corresponds to a block upper triangular thing like this. If it's basic, these will all be one-dimensional, so you're going to get characters again. So you're going to get a picture like this. And so you're going to get the same formula for the eigenvalues. So that's how they computed the eigenvalues for the Settlin Library. Because that monoid is basic, has a basic algebra. Moreover, that monoid has the property that every character takes on non-negative values. So you get the eigenvalues are all non-negative. It was unknown and completely not understood why, when you do the random to top shuffle as a random walk on the group, you actually get non-negative eigenvalues. Because the group characters go plus and minus. So it's like a surprise. John Dixon, who's a famous group theorist, said to me he never understood why those things were non-negative. But this semigroup tells you why. There's also some nice stuff. I don't have time to talk about it. Diaconis and Brown, and later Brown, showed that for very large class of semigroups, which includes all the ones they look at, all random walks are diagonalizable. And again, they're using the representation theory of the semigroup. And it's completely not obvious because there's no reason why this stuff should disappear. It's not a direct sum of simple modules. He does something quite clever. So anyway, the representation theory has been used by people who are real probabilists to study these things. And they always assume, this is the amazing thing, M satisfies, they meaning the guys who are doing all the analysis on semigroups, satisfies that every element is idempotent. So it's as far from a group as you could possibly imagine. Like the example I said there, once I move one to the front, if I try to move one to the front again, one is already at the front, so it doesn't do anything a second time. So they actually studied everything as idempotent. So the characters, if you think about it, a homomorphism from an idempotent monoid to C can only take values 0 and 1, because 0 and 1 are the only idempotents in C. That's why all the eigenvalues are non-negative. Completely trivial. Okay, so unfortunately, I wanted to give more examples, but there's only a finite amount of time. Okay, so anyway, from what they're doing, it's clear that monoids with basic algebras are useful for studying random walks, but they restricted themselves to this case, in part because with this case, you don't need to know any semigroup theory to figure out the representation theory. You just have to be smart. And Ken Brown and these guys are smart. But to actually do this for all monoids with basic algebras, I think would be impossible if you don't know semigroup theory, because you have weird stuff happening. So we figured out basically which monoids have basic algebras. Not actually motivated by this, we had different motivation, and then we ran into this stuff and said, hey, now we can do a lot more random walks. And then once you develop the character theory, you can do all this kind of stuff. You can also compute the multiplicities of all these characters because these eigenvalues have multiplicities, and that's not trivial to do. But that was our motivation. So monoids with basic algebras. So, okay, well, I should give some examples before I tell you how to solve them all. Okay, so here's example number 1. This is the example of the semigroups that were used by Bidigare, Hanlon, and Rockmore. They're the hyperplane arrangement semigroups. So you draw a central hyperplane arrangement. This is the only one I can draw. I could draw one line too, but I'm going to be more advanced. And from this you get a decomposition of the complement of the arrangement into like sectors. And then these sectors have faces. So I don't know if this is probably pretty familiar to people. Anyway. So you have these chambers, and this chamber has like 2 faces, F1 and F2. That's what you get from a hyperplane arrangement. Okay, now the color comes in. So Jacques Tietz, in his work on buildings, constructed a semigroup structure on the faces of this arrangement. But he doesn't tell you it's a semigroup. He proves the associativity, but he writes it in such a weird way that nobody recognized for 30 years it was associativity. Guys who do linear programming also discovered this bland, and guys who invented oriented matroids. So let me explain to you how you multiply the faces. So suppose I have a face, let's call this chamber C2, and I want to compute F1 times C2. So the way you compute the product is you choose a point in F1, you choose a point in C2, it doesn't matter what you choose. You draw the line segment connecting them, and you walk epsilon from F1 to C2. So you have a guy standing here, and he walks up on this tightrope, and goes epsilon, and he lands inside of a chamber, in this case, which is C. That's the multiplication. So you choose a point in each of the 2 faces, and you walk epsilon in the direction from the first face to the second. You will fall off certain hyperplanes, and others you will not fall off, and this will give you a product. And this product satisfies x squared equals x because these faces are convex, so if I have 2 points in the face, it doesn't fall out. It also satisfies, and this is the criterion that these guys also want. I lied slightly when they said that. It satisfies this because if you start walking towards C2 and you change your mind and say, now I want to go back home, it's too late, you've fallen off. You've fallen off. Okay, so these semigroups which satisfy this are for some reason called LRBs. I'm not going to tell you what the LRB stands for. Semigroup theory, everything has a bad name, including the subject. But anyway, it turns out oriented matroids are LRBs. All sorts of combinatorial structures are LRBs. If you look at the definition of an oriented matroid, it's exactly an LRB with some extra properties. Okay, so they use the representation theory of these things to study random walks. So their random walks are random walks on the chambers of these hyperplane arrangements. Okay, the next example I want to give before I try to state some results. I know I wasn't going to get very far to read. Is another example of a monoid with the basic algebra I like is the 0. Oh, this is the bad color. I don't know this color's so bad. The 0 hecamonoid is another nice example. Okay, so let me just tell you what this is. So let W S be a finite Coxeter system. Okay, so then that means W is given by generators S, relations S squared equals 1, and braid relations in braid form. Okay, then the 0 hecamonoid of W, H0 of W, is you take the same presentation, but you just tweak it slightly. So instead of S squared equals 1, S squared is S. Where the term comes from is if you take the Heca algebra and you put Q equals 0, and you change the generators by their negatives, you get the algebra of this monoid. Okay. There's also a nice geometric description of this monoid where I can steal the same picture. So if you have a Coxeter complex for your Coxeter group, which is basically this picture, then there's something famous in the theory. So the generators of the Coxeter group reflect over these walls. But there's something that Ken Brown spends pages on called folding over the walls, where you sort of fold this side here, but this side stays the same, which is an idempotent map. And this Heca0 Heca-monoid, just the monoid generated by folding over the walls of the fundamental chamber. And basically all proofs in Coxeter group theory work for this. So Titz's solution to the word problem, so the Coxeter group solves the word problem here. And there's a bijection between the group and the monoid. They have the same number of elements. But the monoid is better, because the Bruhat order is compatible with the multiplication of the monoid. So for instance, there's a 3-line proof of the Bruhat order, of the Möbius function of the Bruhat order on the Coxeter group using this monoid. So it's very nice. And this has a basic algebra. And you can use the representation theory of monoids with basic algebras to compute its quiver and everything, although it was actually done before that. But it's a very special case. Okay, so those are some examples. So now I will tell you which monoids have basic algebras and what we know in a nutshell with no details because I'm running out of time. I don't actually know when I stopped, given that we started at a slightly strange time and I don't know how long the seminar officially is. So just, you guys can tell me when, and I just want to know in advance. It doesn't matter how, if you say 5 minutes, that's fine. Just.
I think it was 10:37.
So when should I stop so I just know?
11:37.
I should stop at 11:30. Oh, I have that much time. Oh, okay, I can maybe say something. Okay, so the first question is, which monoids have basic algebras? And then I will try to tell you a little bit about what their representation theory looks like, no details, and what things we know how to do without telling you how it's done. Okay, so which monoids have basic algebras? In other words, so I need 2 definitions from monoid theory in order to state the result. So definition 1. Idempotence, E and F. So this is my notation for idempotence. Everybody knows that E stands for idempotence. I guess for the same reason it stands for the neutral element of a group. Some German word. EF, okay, idempotence are conjugate if there exist A and B and M with AB equal to E and BA equals F. Of course, all idempotents in a group are conjugate because there's only one. Just remember, a finite group is a finite monoid with exactly one idempotent. It's a good exercise to give your finite group theory students. As soon as you have one idempotent, a finite monoid is a group. Okay, so that's what it means to be conjugate. Okay, and now why would this be natural? If you think for a second, any character of the monoid will have to agree on E and F because the trace of AB is the trace of BA. So it shouldn't surprise you that these guys are going to behave the same with respect to any representation. So that's why we need this definition. I also need the following fact that the E, F are conjugate. Don't worry too much about it. If and only if, I don't know I need the fact, but I'll just say it anyway. The 2-sided ideal generated by E is the same as the 2-sided ideal generated by F. And I also want to say this one. ME is isomorphic to MF as left M sets. So the second thing is the analog of the ring theoretic result that AE is isomorphic to AF if and only if this holds. This condition holds in the ring. And this is also analogous for finite dimensional algebras, something that's true for rings, and all the proofs are essentially the same. Okay, so now I need a definition, and then I can at least state which one guys are upper triangularizable. So definition, so GE is going to be the automorphism group of this left M set, so just the M equivariant permutations of ME, which is equal to the group of units of the monoid EME. So EME is a monoid with identity E, just like in ring theory when you take a corner. And it's exactly the endomorph. This EME will be the endomorphism monoid of this left set by the same proof as ring theory. Okay, so corollary is E conjugate to F, which I should have made a notation of, implies GE is isomorphic to GF because the M sets are isomorphic, so their automorphism groups are the same. Okay, It's not the way these things are ever defined in semigroup theory books, but it's the fastest way to define it. Okay, so let me tell you what the theorem is. And so this was proved in a paper by Almeida, Margolis, me, and Volkov. M has a basic algebra. M is a finite monoid. If and only if 1, each conjugacy class of idempotents is a sub-semigroup. So that means if you multiply 2 conjugate idempotents, you'll get another idempotent which is conjugate to the guys you started with. This is entirely a semigroup theoretic condition, satisfied automatically by any group because there's only one conjugacy class. And 2, GE is a B-lin for all E. This is just a reflection of the fact that a group algebra is basic if and only if the group is a B-lin. This is a group theoretic condition that's forced-like. So these two conditions are the same as having a basic algebra. Easy to check on your limit. You can just check it instantly. Okay, so we know what they are. Now, to check out how non-trivial semigroup theory actually is, it's not so easy to prove that if you have that if every element is idempotent, then these two. Well, condition 2 is obvious if every element is idempotent because GE will be trivial. But condition 1 is not so easy to see if you don't know the structure of semigroup theory. I don't think it would be a trivial exercise for someone who doesn't know the structure of semigroup theory. But it's true. Okay. I guess another theorem is that you can prove CM is basic if and only if M has a facial representation by over triangular matrices. By over triangular matrices. It's not as obvious as you think, but it's not that bad. One direction of this is trivial because if CM is basic, CM has a faithful representation by upper triangular matrices, so clearly M does. The other way you have to do something. But I won't tell you what we do. Okay, here's another fact. Let E1 through En represent the conjugacy classes of idempotents. Okay, then the radical quotient is isomorphic to the direct product of these group algebras. And these are commutative groups, so this is clearly a product of copies of C. Not only is it isomorphic, but we know what the isomorphism is, and it's essentially induced by a product of semigroup homomorphisms. Except some elements are allowed to go to 0 as well.
Could you read that again?
CM modulo the rats.
Let what?
This?
No, this let. Yeah.
Oh, let E1 through N represent the conjugacy classes of idempotents, which is 1 from each conjugacy class.
Okay.
And the radical quotient is a direct product of those associated group algebras. And the map is very explicit, and it basically sends a monoid element either to a group element or to 0 in each tuple. So from this, this gives the characters right away. Because as long as you know the characters of the leading groups, you know the characters of these monoids. So you can compute all the random walks that these guys wanted. I mean, you understand the semi-simple quotient, so you know the whole semi-simple theory using group theory. Okay, so what other things can we do? But I won't try to describe how we do it. So, what can we do? I won't tell you how we do it because there's no time. What we can do. Of course, sort of our main goal would be to get a quiver presentation because then you can apply all the finite dimensional representation theory. But we don't know how to do that yet. But what we can do is we can find the quiver. We can compute the quiver. Of course, you have to understand what that what does this mean. So we have a better way than just doing linear algebra in extremely high dimensions. So essentially what we do is we construct, what we do is show that computing the quiver is the same as decomposing certain modules over groups. Certain modules, which are explicitly constructed over group algebras of the form of this cut type. Oops, this is so wrong. where these ER and EJs are from here and could be the same. So we construct certain modules over this group algebras, and decomposing these is equivalent to computing the quiver. And so you can do it because we've learned us how to decompose group representations. And I'll just mention the main thing we use is a way of reformulating computing the quiver in terms of computing Hochschild cohomology, and that's essentially what we really compute is Hochschild cohomology. But I don't have time to say how we do it, and probably nobody wants to know. All right, what else can we do? We can compute the Cartan invariance. This is another thing people want to usually do with algebras. Okay, so what are the Cartan invariants? So the Cartan, so the associated to any, say, finite dimensional algebra, there's a matrix called the Cartan matrix, which is the change of basis matrix for the Grothendieck group between the simple modules and the projective and decomposable modules. But I can say this more fancily, less fancily, define Cij to be home dimension of home Pi, comma Pj, or Pi, or P1 through Pn, maybe call it Pm, don't want the same n as there, are the projective and decomposable modules.
Change of basis if the global dimension is finite.
Yeah, change it. Sorry, if the global dimension is finite. Okay, you're right. It's the map that sends, it's the matrix for the map which sends projective and decomposable to the sum of its composition. Yeah, it's not a change of basis unless it's invertible, which is the same as finite global dimension. Einstein corrected it. As projective and decomposable modules. So that's what it is. And this is just the number of times that Pi, the simple module Pi mod rad Pi, appears as a composition factor in Pj. That's what it boils down to. Okay, so we can compute this. I'm not going to say how we do it or what the answer is, but we can compute it. We have a formula that involves the Möbius function with some lattice and some character values of groups. So we have some explicit formula for it. All right, what we can't do. So this is what we can't, what we would like to do. We don't know how to find an admissible ideal. We can't find an admissible ideal. So we can't find a quiver presentation, even though we can find the quiver. I mean, I should mention in all the main examples, the zero-Heckel monoid, the hyperplane semigroups, these groups are all trivial. Those semigroups, all the groups are trivial. So this is just computing. So these modules, they're just talking about vector spaces, and the decomposition is a dimension. So the quiver is really easy to compute for all those guys. Nonetheless, we have no idea how to get a quiver presentation. We don't know in general how to find complete sets of orthogonal idempotents, of primitive idempotents. We don't know how to find these. Maybe we don't want to. So there are several schools of people in algebraic combinatorics who became interested in computing primitive idempotents for some of these guys for various motives. And the best known results up to date don't go anywhere near this whole class. And like the computation, like for very explicit examples, runs over 3 pages, and they do everything in Sage to get outcomes. So the primitive idempotents don't always have a nice form. But I should mention that in the case of these hyperplane semigroups and related semigroups, you can use the primitive idempotents, which are known to actually write down the eigenvectors for the random walk, which is something that gives you a lot of information. So they can be useful if you can get them. And I guess the last thing that we don't know how to do, well, there are many things we don't know how to do. I guess I can list things we don't know how to do almost all day. Describe projective and decomposable modules. Okay, what do I mean by describe? Well, one way to describe them would be find primitive idempotents and say they're the algebra times the primitive idempotents, but that is not very useful. Even if you know the primitive idempotents, you really have no idea what it means to multiply elements of the algebra by weird alternating sums of stringed elements. But there are many examples where we actually do know the projective and decomposables explicitly as a representation, but not for all these guys with basic algebras. We know them for a large class of guys, but not for all. What other things would we like to know? Global dimension. So the global dimension is just the supremum of the projective dimensions of all modules, which is the same as doing it for simple modules. They don't have to be finite global dimension. Semigroup algebras do not have, groups have global dimension 0. Group algebras, semigroups can have infinite global dimension. But there are nice classes of semigroups where it's none, the global dimension is finite, and some classes we can even compute them. But it turns out, so we know for hyperplane semigroups, this was computed by Ken Brown's student Saliola, and it's really beautiful because he interprets these. He interprets these projected dimensions in terms of the topology of the cell complex you get by intersecting the sphere with the hyperplane arrangement. He gets a resolutions from the modules from that. Actually, Brown and Diaconis already did it, but he proved that those are minimal projected resolutions. We also know it for what I call LRBs, which have that weird identity. Again, what we use is topology. We use basically equivalence theorem A. We interpret everything in terms of classifying spaces of small categories. So this is already quite heavy stuff to do simple examples. So we have no hope what to do in general. Okay, and there are lots of other things we'd like to do, but we have a lifetime left, I guess, to do them. So that's, I guess, all I'll say. Oh, yeah, I should say, also another thing we'd like to do is find more nice random walks. Random walks that don't fit into class that people already looked at. So I have some work in progress with Diaconis that's been in progress for a long time because he's busy and we live on opposite sides of the world, but one day we'll finish where we look at random walks on upper triangularizable, on these monoids with basic algebras that are not groups and that are not these idempotent guys that are somewhere in between, and we have some card shuffling type examples. We want more.
Are there any questions?
Do you use any Lie algebra theory in any of this, like for solvable Lie algebra?
I have never used Lie algebra theory in anything I've done, but that's a flaw on my part. I mean, you of course associate any algebra, associative algebra of a Lie algebra, and you would guess that one should be able to use some of this stuff. And these upper triangularizable guys are related, obviously, to solvable Lie algebras. I mean, I didn't mention this because I was talking about finite groups, but it's a fact. This condition number 1 that I wrote down, which is now erased, this condition that conjugacy classes form a semigroup, for an algebra connected out for an irreducible algebraic monoid, this is equivalent to saying that the group of units is solvable. Yeah. So for algebraic monoids which are irreducible as a variety, that condition that conjugate idempotence multiplied to another conjugate idempotent makes the group of units solvable. Actually, you can get away with slightly weaker than that, but okay. It implies that, but the converse is slightly weaker. But anyway, it's more or less morally true. So it is related to solvability in a sense. It's a generalization of solvability.
Okay, so let's thank Ben for his very interesting talk. We're sorry again for being late. It's just accident. Sorry about that.
Oh, it's okay. I thought I was going to be late.
We're going to lunch upstairs.